semiconductors are the most exciting place to be at the moment. They underpin everything.
From EE Tech and All About Circuits, this is Moore's Lobby. I'm your host, Daniel Bogdanoff. We don't have a modern electronics industry without semiconductors and integrated circuits. And usually the focus of IC discussions is around the latest technology nodes, or maybe we're talking high NA EUV lithography, but that's not what we're doing today. We're going a totally different direction. We're exploring flexible chips, not flexible PCBs, but flexible integrated circuits. We're joined by Scott White, the founder and executive director of Pragmatic Semiconductor, and we'll explore how they're making flexible ICs that don't rely on silicon, have a crazy fast fab time, and why you'd want a flexible chip in the first place. Scott, thanks for being here today.
That's great to talk to you.
So I'm curious, how did you first get into technology and what gets you excited about tech?
So my degree was actually technical originally. I ended up doing a degree in mathematics and computer science, mainly because I was good at it and didn't really know what else I might want to do. My first job, funnily enough, was not then in technology. I ended up working for McKinsey as a management consultant. Again, to a certain extent, because I really didn't know what I wanted to do, other than that just being involved on the science side to me wasn't exciting enough. It was sort of interesting technology, but without having a link to the real world, that really didn't have enough excitement. So spending a bit of time effectively working with businesses, understanding their problems, helping with strategy and so forth, that actually gave me a great perspective to then kind of pull that together. And when I started my first tech company, that was sort of the eye-opener moment for me of, yeah, this is actually what I really enjoy doing. It's taking exciting technology, but connecting it to a business plan and something that can actually affect the real world.
So what made you shift from business consulting to starting a tech company?
It was really a combination of two things, really. One is the consulting side of things I found somewhat unfulfilling. On the plus side, you get to go into major companies and work on their most important problems and actually, help steer how they might solve those. The negative side was when I looked back at my time management consulting, about half of the clients we worked for probably didn't get any lasting benefit. McKinsey perhaps wouldn't thank me for saying this, but and to be fair, it's not really their fault. It's that if the client didn't own the result, then the value really wasn't there. So what I kind of concluded from that was that actually the greatest value here is not in coming up with a wonderful strategy, it's in actually going and making it happen. So I wanted to actually get involved in a company where I could be in an operational role and actually, make something happen. And that then kind of linked to, when I thought about, what kind of company does that make sense? I've worked in a huge variety of companies at McKinsey, from, healthcare to, meat producers to telecoms companies, and so forth. And, the ones that I, was most excited about by generally were ones that were involved in technology one way or another. And that sort of links back to, I'm a bit of a geek at heart. I like mathematical algorithms. I like AI and machine learning, all these kinds of things. So, things that could combine the two. If you can take that technology passion and link it to, a business idea, then that's exciting.
And you were studying AI and the world of machine learning well before it blew up in recent years. I feel like if I were in your shoes, I would have kind of known that had been lurking for a while, maybe, and then to see it be understood by the public has to be interesting to watch that roll out.
Very much so, yeah. So I did my degree thesis was in neural networks and syntactic machine learning back in, when was it? The early 90s. So, it was kind of around, but it wasn't a big deal. It was just, one of a number of things that people were looking at. And yeah, I guess what we've seen in the last couple of decades is, funnily enough, a lot of the basic concepts that we had then haven't actually changed too much. But what has changed is that the hardware technology has caught up to actually make those really viable to implement in real world systems and do real-time analysis. And then, of course, once that happened, then actually, the rate of progress on the algorithmic side of things and the concepts has actually accelerated as a result of that. And now, as you say, we're seeing the public awareness of that also sort of ramping up to another level. So yeah, it's very exciting. It's slightly bizarre because, some of these concepts still feel like they are much the same as what I was researching, a few decades ago, but they've just all been supercharged to a different level. So yeah, very exciting to see that actually happening in the real world.
And then you had a number of startups that you started first in telecom, I understand, and then had a few others, and ended up doing a company called Nano ePrint. Can you tell me a little bit about Nano ePrint?
Yeah, I mean, Nano ePrint was a kind of small piece of that journey, I would say. So yeah, as you say, I started getting into tech startups, tech companies. When I left McKinsey, I joined a telecoms research center, which basically wanted to restructure itself so it could commercialize some of the interesting technologies it developed. So I helped that center set themselves up so they could do that, and then took one of the most interesting technologies through that process to start my first company. And having then built and moved to the Bay Area when I building that company, brought in a good CEO because I at that time definitely didn't have the experience to actually run a company. So I helped sort of get it funded, get the early business plan together, brought in an experienced CEO, and then sort of lived that journey through to early revenues and then eventually selling the business. That was a great journey. So let's go do that again. So yeah, another couple of telecoms companies. But after Azure Networks, which was fairly major success, I really wanted to do something other than telecoms. Not because telecoms wasn't interesting, but it's one small piece of the tech ecosystem. So I was interested in broadening really what I was doing. Got involved in a couple of different companies part-time. So I got involved in Cortexa then, which is a machine learning visual AI company. But one of the companies was a spin-out from the University of Manchester called Nano ePrint, which had some really interesting device-level semiconductor technology. And that was sort of my first introduction into semiconductors as a field. I've done electronics, but not necessarily the sort of semiconductor side of things. It was a great learning experience, put a lot of time and effort into researching the field, digging out old textbooks and actually, making sure I understood terminology and what was important and what wasn't. At the end of the day, Nano ePrint had a number of challenges. I'd say it was, in many respects, a sort of classic academic spin-out. Great, interesting technology, but it wasn't clear that it was repeatable from a manufacturability perspective, and it also wasn't clear that it really directly fit a market requirement. But in looking at that and working with Nano ePrint, what I found was that there was a number of customers we were talking to who were really excited about the idea of can you do the equivalent of a silicon chip, but in a form factor that's dramatically different, something that's thin and flexible, and at a cost point that is an order of magnitude different from silicon. And so although the Nano ePrint technology wasn't really quite enough to solve that requirement, it was the starting point for those customer discussions and then led to the creation of the Pragmatic.
I'm curious, as you went through a few startups, almost full cycle there, are there anything you looked back on, any moments or themes or pieces of advice that you looked back on for your time as a management consultant where you look and go, oh, I really got that right. That was a golden piece of advice, or I really got that wrong. And if only I had known, maybe I would have done things differently.
There's certainly plenty in the latter category. So I guess from the start, if I think back on the business plan I put together for Atmosphere Networks, this first company I spun out of the Telecoms Research Center, it was, I would say, a very good bit of analytical research, and it was almost entirely useless from an actual practical perspective. So, lots of detailed research, good scoping of the market and so forth, but it really didn't necessarily consider some of the most important factors around the practicalities of what you face when you start trying to commercialize a new technology. So, critical technology risks, how do you actually make something that works? How do you drive adoption from the early customers, when it's not just a sort of theoretical concept, but you actually need somebody to put some money into, investing in being the first mover. Some of these, key elements of industry dynamics and business dynamics, and in many cases, interpersonal dynamics as well. The thing I think that is easy to underestimate when you first sort of start down this journey, particularly coming from both a scientific background and a very analytical consulting background is the importance of human emotion in any decision that's made. And that, the bigger the decision, the more emotion is involved rather than fact. So whether it's to do with getting funding for the business or to do with getting, that first customer to place a major purchase order, it is as much about, how do you do the emotional sell as, the facts and the figures and the analysis that underpins that. So I think that's probably the biggest learning for me has been to factor those kinds of things into the thinking process of, of how we want to build, a business or how we, set out plans. And so I hope, in hindsight, I think I've got better at thinking about that as an explicit factor. And so when I'm now looking at an investor presentation or business plan, there's as much focus on the team element side of things, or how do you motivate people, or how do you get people both inside and outside the company excited about what you're doing. These are not just sort of soft, nice to have factors. They're actually tend to be fairly critical to success.
Yeah, the soft skills are always important to keep in mind, but so easy to miss. It's time for a quick break, but Scott, we'll be right back because I'm curious to learn about not just soft skills, but soft chips. We'll be right back. Is electronics your addiction? If so, check out today's sponsor, the Technology Addicts podcast by Avnet Abacus, a leading European distributor of cutting-edge tech products. Explore the exciting world of interconnect, passive, electromechanical, power supply, energy storage, wireless and sensor products and solutions with their inspiring interview guests. With their vast product portfolio, deep industry expertise, and unrelenting commitment to customer satisfaction, they are here to transform your ideas into reality and make you all technology addicts. Tune in now wherever you get your podcasts to the Technology Addicts podcast by Avnet Abacus. And now, back to our conversation with Scott White, founder and executive director of Pragmatic Semiconductor. Scott, semiconductors are one of those things that get a subset of people very, very excited, and the rest of the population doesn't really even know what they are. Could you tell me, what is Pragmatic Semiconductor? What do you do, and how did you find yourself here?
So Pragmatic Semiconductor makes flexible integrated circuits. So you think about the silicon chip, it's the brain of all of our electronic devices. It's wonderful. It's improved dramatically over the last 5 decades or more with Moore's Law, that the podcast is named after, that continual progression of technology and performance. But at the end of the day, you're still stuck with something that is a rigid piece of silicon that tends to then get embedded in a rigid box of electronics. There are ways you can, play tunes with that, but you still have some fundamental limitations from that. So what we do instead is we make our technology from thin film semiconductor materials that can be put onto flexible plastic substrates, which means you end up with a chip that is thin and flexible and can be embedded in just about anything. And as part of developing that, we focused on materials and processes that allow us to do that at a cost point that is an order of magnitude lower than silicon. So we don't actually have the same performance as silicon, or certainly not silicon as it's progressed over the past several decades, but we have performance that is good enough for a certain set of tasks, and certainly very exciting in terms of looking at what people want to do with electronics when they're putting it into things that aren't an electronic product that is a rigid box that you buy and spend hundreds of thousands of dollars on. So a lot of the applications we're targeting are pushing electronics into things that you would never consider putting a silicon chip into. So the easiest to explain example there is smart packaging for fast-moving consumer goods. So you think about everything you buy in the supermarket sits on a shelf in some form of packaging. If you can embed intelligence into that packaging, you can improve traceability of it. You can make the inventory control better. You can ensure that it's not a counterfeit. You can ensure that the right tax has been paid on it. You can interact with the consumer at the point of purchase and even at the point of use of that product by communicating with a mobile phone. You can even actually manage how that waste, that packaging goes into the waste stream at end of life of the product and ensure it gets recycled or reused in the most optimal way. So, this is something that has to be, a novel form factor. It's got to go into thin, flexible plastic or paper packaging. And it's got to do it at a cost point that is a penny or less, because actually that's what packaging costs. And no matter how much value you bring, if it's, if it's going to cost you, $1 to add that intelligence, it's just never going to make sense economically. So, those are the sorts of applications that we developed the technology for. Interestingly, what we've seen, having got the technology to a certain level of maturity, is that in addition to that big class of, if you like, very low cost, high volume applications, we're embedding it into, things that aren't electronic products. We're also seeing two other big sets of opportunities. One is things that really leverage the form factor, but for very high value products. So things like sensors, where you might want a sensor that is thin and flexible because it can wrap around something or can conform to the human body. You can't do that with a rigid silicon chip, but you can without thin, flexible ICs. And that actually creates huge value to do something that can't be done in any other way. And then the other category is just simply replacing silicon. And this was sort of a big shift we saw in the last couple of years as a result of the supply chain crisis induced by COVID. Is that, as we saw that silicon chips are so critical in so many different supply chains, and we have a very significant geopolitical exposure, that the supply is very concentrated, and often it's concentrated in geographies where, maybe it doesn't quite fit with politics. So, there's been this massive trend towards onshoring or reshoring of semiconductor manufacturing capacity. A lot of what you tend to hear in the press and what people focus on is how you solve that problem for advanced node silicon, because that obviously supports the most advanced compute and AI applications we need. But actually, it turns out that when you look at what are the most critical parts in most industrial supply chains, it is not those advanced silicon components. It is very, very simple chips. Automotive is a classic example where, yes, you might need a couple of very high-end AI chips for the self-driving features of a car or to control the engine, but actually, 70, 80, 90% of the chips you find in a car, and that's, 2,000-3,000 chips or so that you find in a typical car these days, most of those are done in mature node, legacy node silicon technologies, because they only need to do a very simple function. The example I always quote is the chip that makes the windscreen wipers work. It needs to do a very, very simple function, but if you don't have that chip, you cannot sell a $100,000 car. And we saw this very explicitly over the last couple of years. It's still happening actually in some of those supply chains, that they're still not able to sell end products because they can't get a 5-cent component that does something that actually is absolutely critical to the end functionality of the overall product. So what we're seeing there is that although our performance is nowhere near as good as what you can do today with silicon, it's actually good enough to replace what you need for some of these simpler components. And we can do that with a supply chain model that is far more controllable and easy to be localized, and to do that in a cost-effective way.
So you don't necessarily need to go to like TSMC and use their latest high-end ultraviolet process if you're just trying to get the car windshield wipers to work. I like that analogy a lot.
Exactly.
Tell me about how this is actually constructed, because when I heard flexible semiconductors, I got just completely nerd sniped and got stuck down this research hole. Can you talk me through, like, instead of basically etching and depositing on a piece of glass, you're doing it on plastic?
So the company name, Pragmatic, is very intentional. The approach we've taken to developing this technology is not a theoretical sort of how do we invent something that's as wacky as possible. It's about how do we solve a very specific problem of making a chip that is 10 times lower cost than silicon and is thin and flexible. And so as we've developed the technology platform, every decision has been informed by, do we need to invent something new, or can we reuse the way things are done today? And it turns out that there is a certain set of problems where you need to get very, very creative. And there are an awful lot of things where you can just say, we can do that exactly the same way that people are used to doing. And so, for example, the way we solve the problem of making a flexible chip, if we had to do that with entirely new processes and entirely new tools, you'd have to invent an entirely new supply chain for everything we're doing, which makes it very difficult to scale effectively. So instead, what we do is we take a glass wafer, a disc, just looks very similar to a silicon wafer that you'd use in a typical silicon manufacturing process today. It just happens to be made of glass because we get some benefits from the transparency. but we take that as a physical carrier onto which we coat a thin plastic substrate, and then we go through all of our process and deposit and pattern all of the other layers on it using broadly conventional semiconductor manufacturing processes and tools from the same vendors that TSMC would be buying tools from. And then at the end of the process, you basically peel this flexible wafer off from that glass carrier, and you reuse the glass carrier for the next wafer that goes through the process. So we get the benefit of being able to use a very well-established supply chain with very mature tools that we know can get the kind of process yields that we need. And they can just view it as a rigid wafer that's going through a standard semiconductor process, but the actual rigid wafer does not form part of our bill of materials. It doesn't constrain the form factor of the end product. So we have this really nice balance of effectively pretty much everything we do is something you would see in a normal semiconductor process. What we don't have is a lot of the very expensive, very long duration, high temperature processes you might find in silicon. So perhaps for those of your audience who sort of are kind of really into semiconductor manufacturing, a fabrication line is broken down as front end line, back end line. Front end line is where you make the transistor and other active semiconductor devices, and back end line is all about connecting those together within the integrated circuit. Most of what we do effectively looks much more like just a back end line process. So we don't have any of the high cost elements that you find in the normal front end line process, where you're trying to take a single crystalline silicon wafer and change the characteristics of the silicon at very small scale in order to create the devices. We do it all via thin film deposition and patterning. And that means we have a process that is very low cost, but also very high throughput, because each individual layer can be deposited very quickly in a matter of minutes, can be patterned in a matter of minutes. So as distinct from silicon, where you find that, a typical wafer manufacturing process from starting with a raw silicon wafer to fabricated circuits will typically take a minimum of 3 months. And actually, by the time you add in scheduling and optimization of process flow, it's more typically 6 to 9 months. In our case, we're looking at about 48 hours start to finish, including all of that scheduling. It's actually well under 24 hours if you just wanted to run one wafer through the process. So that makes a massive difference to how you think about how you can design circuits, how you can optimize the design, because you can actually bring a new product to market so much quicker. It changes a lot of the dynamics around how we structure the fab, because we don't need to plan for having months worth of work in progress going through the line, and how you manage all of that through various batches. We actually have a process that is much more like a build to order kind of process, just in time manufacturing. That changes loads of dynamics around how much metrology you need to do through the process, what your exposure is if the line goes down and you have to restart a wafer. All of these things change the way you think about it. So although we started with this very pragmatic approach of we can use conventional semiconductor manufacturing processes, what we've ended up with is something that looks radically different. And just to give a sense of the difference there, I think everybody kind of knows that typical silicon fab these days costs billions to tens of billions of dollars and takes, hundreds of thousands of, square feet of clean room space and so forth, if not millions of square feet. You need a power station next to it to provide the power. You need all this kind of stuff. Ours, basically, the entire footprint of the fab and all of its facilities is around about 1,000 square meters.
That's it.
Everything. Yeah.
Goodness gracious.
And it costs several orders of magnitude less in terms of capital cost. So we're talking about sort of tens of millions rather than tens of billions for the capital cost. And that's a combination of these, the fact that we have these different material sets, so we don't have the challenges of that front-end line silicon process, but also the entire rethinking of everything else around how you think about constructing a fab when you change some of these dynamics, like how long it actually takes the start to finish manufacturing process.
My wheels are spinning. The idea that I could design a chip and a circuit board on the same day, send the chip to you, send the PCB somewhere else off, and get the chip back before I get the circuit board is blowing my mind.
And actually, it's a really interesting point. This is fair to say not something we envisaged when we started developing the technology, 13 years ago, but what we found is that speed of manufacturing is actually the primary factor that some of our foundry customers are choosing our technology. So forget the form factor, forget the cost, forget all these bits. Just the fact that you can do a bespoke hardware design, a new ASIC, and not have to wait a year or more to get the silicon back, to be able to do that and within a few days to get that hardware back means you can completely change the dynamics of how you think about hardware optimization. And you think about everything in the way we make electronics today is driven around standardizing your chip design so that you can use it for the next 5 years and use software to control exactly what functionality you want to enable on it. You can shift that around. You actually no longer need software because you can optimize the hardware perfectly for exactly what you want in that particular application. It also changes a lot of the dynamics around what you do on the PCB as well. If you think about a typical PCB in an electronics product today, it might have a couple of big chips on it, and then it has 10 times as many small components, what's typically termed glue logic. So, power management circuitry, level shifters, interface adapters, passive components, resistors and capacitors and things. And all of those bits are there on the PCB because it doesn't make sense to try and integrate those into the ASIC when you want to be able to reuse that for as many different things as you possibly can to amortize the cost of having to design it. If you change the dynamics of the cost and time to do the hardware optimization on the chip, then actually you can integrate all of that stuff into the chip and you don't even need the PCB at all.
That's wild. So when I think of building a transistor, for example, I think of running wafers through ovens to grow oxides and etching acids. Can you talk through how would you go about building like a transistor with this type of process?
So the key is that it's a thin film transistor. So as I sort of mentioned before, what you were describing about, the normal things that are expensive in a silicon process are basically where you're trying to do stuff kind of to and within the structure of the silicon. So creating the N-type well within a P-type or, things like that. Yeah, these are the bits that they get expensive because you're having to use a lot of energy, bombard the thing with ions in order to change the characteristics of the silicon. You're implanting new materials into it in order to change its characteristics. By contrast, our semiconductor material is deposited as a thin film layer with exactly the characteristics we need in it. So it takes us a couple of minutes to deposit that layer, and we don't have to do anything to it afterwards. It has, as deposited, exactly the semiconductor characteristics we need. And the same for every other layer in our process. So it comes from that approach of everything we do is basically a very simple process of deposit a thin film layer, use standard photolithography to pattern it, and then go on to the next layer. And so you get this very rapid cycle time of layers without that, the sort of cost and complexity and time of the typical front end of the line process.
So what are some things that might surprise a IC engineer who comes in to look at your process or your line or just your end chip? What might surprise them or what might they find especially interesting?
So firstly, as a starting point, we generally try and make it as similar as possible to what they're used to, because it's the easiest entry point for people to start getting used to a new technology. So sure. If you think about the design process, it uses a standard EDA flow. We provide a process design kit that is imported into the same EDA tools that people would use for a silicon chip design. And it produces a GDS2 model that's shipped back to us for us to run the manufacturing process. So the starting point is you can use this exactly like a silicon process to design a chip in and get your outcome. The things that are different beyond the sort of bits we've already talked around about sort of cost and time is obviously you end up with a thin, flexible chip. Now, that has the obvious benefit of you can stick it into something that isn't a rigid box of electronics, and it doesn't need to be packaged in the same way that you might think about silicon. But there's some perhaps less obvious benefits you get from that as well. The fact that it is extremely thin means that the way you think about assembling it into an end product or connecting it to other components can be very, very different. For a start, we can have much larger contact pads than you might have on silicon because our cost per unit area is so much smaller. we have a very thin circuit. So you can think about how you might wrap that around something you want to connect it to, rather than having to stack things vertically. And so you think about a lot of the challenges that the industry as a whole is starting to wrestle with as it starts to think about 3D packaging and other advanced packaging technologies. One of the key constraints that is always a barrier there is you're dealing with this rigid bit of silicon that has, the functionality happening on the top surface, and then it's got 700 microns of bulk silicon sitting underneath it. And you need, typically to figure out how you connect these things together efficiently and how you stack them and, how you actually make that work in a viable way. And what we're starting to see in some of our discussions around sort of hybrid applications where people are using our technology, not necessarily as a direct replacement for silicon, but actually alongside advanced silicon to complement it and get the best of both worlds, is that taking advantage of that thinness and that flexibility provides some unique benefits in how you can think about the packaging of the complete solution.
So are the Flex ICs, are they generally the footprint is a lot larger than what you think of for a normal IC?
It tends to be. It doesn't have to be. So if we think about something where the footprint is not determined by an application, then what we will generally find is our technology is not as dense as conventional silicon, so it tends to have a larger footprint. But what we also see is that generally that larger footprint actually saves cost elsewhere in the process. So if we take one of our main application areas around radio frequency identification, for example, RFID is a fairly simple mixed signal chip. And so if you get a silicon RFID chip, it is incredibly small. They are down at the level of about 0.1 of a square millimeter. So that's kind of the size of die you're dealing with. Now, that's been shrunk to that size because that's the way you optimize the cost most in silicon, is make the thing as small as possible. You run into a number of challenges, though, which is how do you dice a chip that small effectively without losing so much in the dice lines that it actually impacts your cost structure? Once you've diced it, how do you handle a chip that small? How do you place it accurately? Particularly when in the area of RFID, you want to place that onto a reel of antennas. So you've got a roll-to-roll process with a large structure antenna that you're trying to place this really, really tiny chip onto with an appropriate level of accuracy. Now, the industry has solved all of those problems, but of course, the solutions have cost embedded in them because they are trying to solve this challenge of how you connect a really, really tiny chip to a moving web of large antennas. And so when you sort of change that dynamic and say, actually, you could have a larger chip that is also flexible. So now you can think differently about how you might connect that to the antenna. How does that impact the way you design the antenna? Your contact pads can be patterned less accurately, for example. The placement accuracy can be relaxed. Maybe that means you can speed up the process. Maybe it means you can place multiple chips at the same time. All these sort of different ideas around how you change the dynamics by taking advantage of the fact that the chip is physically larger without having a cost penalty associated with doing that. So that's one class of applications. We also see, however, that there's many applications where the footprint is dictated by the application. So a good example here is something like a fingerprint sensor. Fingerprint sensor has to be roughly the size of your fingertip. Doesn't matter how simple the circuitry is, you can't make one that's a fraction of a square millimeter because it doesn't cover everything of your fingertip. So, very simple idea, but this is one of the reasons things like that are so expensive today, is because the only way to solve it is to use quite a large area of silicon to do a task that is nowhere near as complicated as the functionality you could pack into a square centimeter or so of silicon. And so in those applications, we see that we can offer sort of direct like for like exactly the same footprint. There's still plenty of space within that to fit in the functionality, even with some of the things that are not as dense in our technology. And then we get sort of full advantage of the lower cost per unit area, as well as, of course, the interesting potential of taking advantage of the flexibility and thinness to be able to put that somewhere that you might not be able to put a rigid square centimeter of silicon.
Does yield become a concern then when you're going much bigger like that?
No more so than in silicon. So, as with any semiconductor process, your yield goes down as the circuit footprint goes up because there's more chance of a defect in the process happening to fall within the IC. There are some design techniques that can mitigate those, but essentially it's no different from our technology compared to silicon, is that, the yield model of the entire process has to be good enough that, you can accept either a certain level of defectivity or a certain level of yield loss and still have the process make economic sense. But for us, that's generally much easier because the process is so much faster and so much cheaper that, you can actually, you've got more flexibility in how you balance those different factors.
So you mentioned that you can get these out really, really fast, like astoundingly quickly. And you also mentioned earlier you were part of a startup that was like a classic academic spinoff. When it comes to volume manufacturing, what does it look like to spin up a process for these that gets you the volume you need?
As I mentioned before, pragmatic, our kind of philosophy from day one has been a pragmatic approach to, not inventing stuff we don't need to. And a lot of that's been driven by thinking forward to the challenge of how do you scale manufacturing and do that with a supply chain that's robust, with a model that's going to get the right yield, the right consistency, and so forth. So for us, the key milestones in our journey have been not just kind of inventing the technology and getting the first few patents and showing it can work, but more importantly, getting that into our first fabrication line and showing that we can run that with an appropriate level of consistency in the process. So we have today our first fabrication line in the northeast of England, has been operational for a number of years now. It's a 200 millimeter, 8-inch wafer-sized line. We have just finished installation of our second fab, which is taking that to 300 millimeter, so state-of-the-art 12-inch wafers. And that is now producing, albeit we haven't yet released to commercial production. So we're in sort of final stages of stabilizing and qualifying the process there. But in essence, the process of bringing up and qualifying a line for us is much the same as in silicon. We have a process that we know works, but you implement that on the set of tools in the fab, and it requires tweaking some process parameters and pulling some levers to make sure the entire process works stably over time. And that's a more or less a never-ending task for the operations team. They even once it's working, they continually tweaking that to optimize it and get every extra little bit of yield they can out of the process. So for us, because we've taken that approach of saying, let's build a process that can use the same kinds of tools, the same kinds of processes as you see in conventional semiconductor manufacturing, what it means is we can therefore have that, confidence of ramping up a fab goes through exactly the same kind of process, with the benefit in our case that the learning cycles are that much quicker. So if you think about bringing up a silicon fab in a new silicon process, every time you run a new process variation, you've got to wait 3 months before you find out whether it did anything good or bad. We're getting that learning cycle in a matter of days where, you tweak something in the process, a few days later, you already know what it did. You can run multiple lots through within the space of a week to know statistically has that improved the process on.
When you go to build these lines and you're talking to the companies that build semiconductor manufacturing equipment, what is their reaction to what you're doing? So,
the first reaction is obviously a little bit of, stunned silence is probably the most common reaction, particularly when we talk about the sort of scale at which we're starting to ramp this. But actually the interesting thing is that they really like it, because if you think about the dynamics of the semiconductor manufacturing industry, it's always been a very cyclical industry. There's the crisis we've had in the last few years where it kind of went from, kind of massive oversupply to massive undersupply and now starting to correct. That's hit the headlines. But actually, if you go back through the history of the industry, it's had a series of these things. They've just never been quite as critical because chips haven't been as critical in so many industries. And it was a more extreme shock as a result of COVID in the last few years. But every 5-10 years, we've seen this move from oversupply to undersupply. You get into undersupply, then everybody invests in new fab capacity, and then a few years later you end up with oversupply because there's this huge lag time in building that new capacity. And so The challenge for the equipment manufacturers has typically been that they cannot scale their supply chain to deliver what the industry needs in the boom times, because it knows that 5 years later, nobody's going to be ordering fabs. And so, they need to kind of smooth out that demand. And as a result, what we see is that in downtimes, they can deliver equipment very, very quickly. But actually, when you get into the crunch under supply, when everybody's trying to build fabs, lead times for semiconductor equipment can push out to 24 months or more. And so I think the opportunity that we interestingly offer them is that because we have a much more rapid process, and we've talked about the speed of the manufacturing process, but it turns out because of the simplicity of our fab model, the time to build a new fab is also that much quicker. So we're talking about something in the region of about 12 months to build a new fab from scratch.
Wow.
And so that means that it's much more predictable for the equipment manufacturers. So at the moment, we're obviously building, one fab this year. We've just started building our third fab as well. This will ramp up slowly, but you play this forward a couple of years as we ramp the business, and we're going to be building multiple fabs every year as we expand this. It's very modular, if you like, in the way that capacity expands. And so, supply and demand will shift around a little bit, but because we're growing demand incrementally, we can actually adapt that very quickly. Instead of building 10 fabs that we think we might need, maybe we'll only build 8, or maybe we'll actually build 12 if demand's growing slightly slower or slightly quicker than we thought it was going to. We can adjust that, and we can adjust that quickly enough that within 12 months, we've adjusted the supply to match demand. So potentially this gives the equipment manufacturers a much more predictable demand side for what they're doing, and therefore allows them far more flexibility in how they plan their supply chains and how they manage that over time. So, this is obviously still to develop, and we're not yet at a scale where that statistically is coming into play, but it's certainly one of the reasons why we've had been able to build very good relationship with some of the biggest semiconductor equipment manufacturers in the world, is that they see that as we scale, that actually has the potential to make their business a lot more predictable as well.
12 months to build a fab is so fast. That's just insanely fast.
And you can build it anywhere. So, I haven't talked a lot about the fab side of things. I talked about some of the things we change in the process, and that means you need fewer tools in the process. The reason it's far smaller footprint is because we have fewer process steps, which means you need less equipment. We have faster cycle time, so you need less metrology to check things before you spend another 3 months making the wafer, things like that. And so as a result, what we have is this modular approach to capacity expansion, which means you can put a fab pretty much anywhere. Our new Pragmatic Park site in Durham in the northeast of England is a good example. This is an old industrial pipe manufacturing facility that we've converted, and we're now using a tiny portion of it for our second fab. But it's using standard town water supply, standard industrial electricity supply. It doesn't need the same infrastructure that you need to consider if you're going to put in a $10 billion 3-nanometer silicon process. So when we look at how we're expanding capacity over time, we will have some level of concentration because it just makes our life easier if we have more capacity in one place. But over time, what we're seeing is that we will actually distribute our capacity around the world as close as possible to where our customers are. We've even got a model we've developed, which a number of our customers are really excited about, which is called Fab as a Service, where we could put a fab on site within the customer's premises to give them dedicated supply for what they need, complete local manufacturing, security of supply. They get to choose what chips they want to run on a daily basis. 2 days later, it comes out the fab, and they've got complete control of that. It's not kind of, somewhere on the other side of the world where they're worried about, what might happen in terms of geopolitics or what might happen in terms of shipping lanes getting blocked and, all these other things that have sort of impacted supply in the last few years. So if we play this forward 5 or 10 years, that's the model we're aiming for is, having 50 to 100 fabs scattered around the world in different places, and probably a significant portion of those will be on site with our largest or most strategic customers, giving them that security of supply that they need.
Yeah, there's so many situations where I can imagine having the fab next door be a really useful, helpful thing. I've seen it in my work, where we have if there's a fab below my feet where I normally sit, and that's a super useful thing for our teams. So it sounds like you have a pretty good vision for the future of Pragmatic Semiconductor. Can you talk about how you're going to get there, and maybe expound a little more on what you think the potential for this is?
Sure. So we've just closed in December, or first close on our Series D funding, which was about $230 million. Actually, the largest ever venture funding round for a semiconductor company in Europe. So we're very, very pleased about that. But most importantly, that gives us the capital to invest in continue to scale our manufacturing capacity. So it'll directly fund our next couple of fabs to allow us to continue growing the manufacturing side of the business, and will take us to profitability so that we can then continue growing organically from there. In terms of how we actually will be doing that, our near-term focus is to continue scaling the business within the UK. So we have a global customer base, both for our RFID products and for our general foundry services. But at the moment, our first two fabs are in the UK, and we expect to, in the near term, to continue scaling there, just mainly because it makes life easier for our team to sort of concentrate all of the resource and the know-how and so forth. But as I alluded to before, with the things like the fab as a service model, as we continue to grow the business, we expect to then start building fabs in multiple places around the world that allow us to drive that localization of supply for our customers. The fabs are fully automated, so that means we can basically centralize all of our know-how, with our team in the UK to be able to manage those fabs, collate all the learnings from those, ensure that we build best practice across all the different lines and so forth, and to be able to run the process consistently so that regardless of where the fab is in the world, you're getting exactly the same quality of wafers coming out of it. So our plan is really now a combination of execution on operational scale-up of the manufacturing side of the business alongside continuous scale-up of demand and applications. And so on the latter category, leveraging the foundry model, which is obviously very well proven in the silicon world, to allow customers to be as creative as they want in using our technology for a wide variety of different applications.
If you had a magic wand and could fix or change or adjust something either in your process, one of your technical challenges, or something in the semiconductor industry at large, where would you wave that wand?
Oh, that's a really good question. How many wands am I allowed?
As many as you want in this case.
I mean, there's always sort of things in the detail where we say, well, actually, this is our headache today, and I'd love to wave a wand there, but actually we know we'll solve that particular challenge, and there'll be a different one a month from now. I think from a broader perspective, one of the biggest challenges we have is around building the ecosystem around our technology. So we have taken the approach, as I mentioned before, of generally trying to not invent things we don't need to invent. And part of the reason for that is to be able to leverage the existing very rich ecosystem around the silicon industry on the design side, for example, and test and so forth. But having said that, because we've got a product that is different, it can be thin and flexible, and you can optimize the functionality much quicker. Although we can use that existing ecosystem, it's not necessarily exactly optimized for what people might want to do with our technology. So one of the things we need to do over time is continue to work with that ecosystem, help them understand where our technology can be different, what advantages that can bring to other parts of the ecosystem in order to accelerate things. And so, back to the question of sort of the one bit, I guess the two areas where we know this will happen over time, but if we can wave a wand and make it happen quicker, it would really accelerate a lot of use cases for our technology. One part of the ecosystem is around the sort of assembly side of things. How do you take advantage of a thin, flexible chip and assemble that in a way that is different from how you assemble a rigid silicon chip? There's so much potential there, but it's stuff that nobody's thought about doing before because it's all been about pick and place of chips and packaging them in ceramic or plastic packages so they go onto a PCB. So there's an evolution there of, well, if you think about a flexible chip going into a flexible wearable application or an on-body sensor, how do you actually assemble that in the most efficient way rather than just leveraging the kind of the ways they've been developed in the past for handling rigid components. So that's one piece that will evolve, but I'd love to have a magic wand to make it happen quicker. At the other end of the spectrum, I think around the design side is where there's also scope for innovation. So we've talked a bit about the benefit of our technology of being able to go from a new design to manufacture that really, really quickly and without the high tape out cost of conventional silicon. So that's all great. But actually at the moment, the thing that to a certain extent gates that is that if you've still got to spend as much on the design tools and the EDA flow and take just as long designing it and need a really experienced chip designer to do that because they're the only ones that know how to actually run the EDA tools, that actually constrains things. What we'd really love to do is properly democratize access to the technology. If you could have something that was built potentially on an open source EDA platform that had the right level of abstraction, so any software coder that knew how to program in C could effectively write some code, press a button, and that gets turned into a hardware design for the chip that runs that. That's where we'd love to get to. And again, there's a lot of that's happening in some of the work we're doing with the ecosystem, but it's not there because actually it doesn't kind of make sense with silicon to do it that way. Silicon's been driving towards progressively more and more complex chips, so that the design tools are getting more and more complex. And actually what we want to do is enable the simpler things that people want to do to be just that much easier and more accessible for a greater range of designers.
Yeah, there's definitely a subculture of momentum moving towards custom ASICs, that democratization of custom ASICs, but it still right now relies upon someone like a Google to put together a wafer run.
Exactly. There's the free open source silicon stuff that Google and their partners have tried to do, and that still suffers from having to have a fixed schedule of multi-party wafer tape outs and things like that. So we can, if you like, we sort of solve the back end of that, of how do you reduce the cost and the time of going from tape out to product and actually be able to link that to volume as well. So it's not just getting one or two components, but actually you could then very quickly ramp that into volume. But it's still got that challenge at the front end of, well, how do you design something in the most efficient way so that what you really want is the same cycle you have today for software where you can do that. We're not quite at that point. We are surprisingly close to that point. We've got customers that are doing basically multiple iterations of tape out. So every 3 months they're doing a new tape out. And within that 3-month cycle, they're going from design spec to designing the chip, taping it out. We manufacture it for them. They're then testing it, analyzing that, and using that as then the input into the next phase of specs. So that's ridiculously quick given what we're used to in the hardware world, but it's still a little bit slower than a 6-week agile software design cycle. So what we'd really love to do is if we can compress the front end of that and actually make the design side of the design piece of that cycle quicker as well, then we could get that entire iteration cycle down to something that is effectively equivalent to what we do today in agile software development.
It's exciting. It's very exciting. As we wrap up, we like to do a lightning round at the end of these episodes. As someone who studied AI and you've been in tech for a while now, are there any examples of pop culture, sci-fi movies, books, whatever it might be, that really get technology right, or any in your mind that really get it wrong?
I wouldn't say there's any that are kind of all one or the other. I think to me, I've always been a fan of sci-fi, and I think the beauty of sci-fi is it's sparking the imagination. There's so much stuff that we can do that wasn't envisaged in those older sci-fi, but there's a bunch of stuff that we haven't got to yet. So I would kind of look at it and just say, it's the stuff that we haven't achieved yet that's in sci-fi. That's the sort of inspiration for what can we do next.
When you look forward 10 years, are there any possible but surprising applications you could see for your pragmatic technology?
Yeah, I think one trend that is quite exciting, but is going to take a while, is embedded electronics, sort of in-body electronics. We're starting to see quite a lot of on-body, where thin flexible sensors and so forth can add a lot of value, but actually embedding it within the body, neurological sensors, for example, sensors that could actually connect to the brain, that we can conform around the brain in order to connect to it in the right way. That's something that I think is hugely exciting, in both from a healthcare perspective as well as some of the more wacky, sci-fi use cases that people could come up with for that. But yeah, I think there's things like that will create entirely new categories of product that don't exist today.
I've thought about like the embedded NFC chip in the hand that people have done, but I don't think I'm quite cyberpunk enough for that yet.
Well, an NFC chip is, I've seen that as well. And it's not quite, the value you get from it isn't enough to warrant embedding it in your body.
Agreed.
Because I think if you look at sort of some of the healthcare benefits that you can get from that, you look at what can already be done with artificial organs and things like that.
Yeah.
But, those work because they are, again, boxes of electronics effectively. So, where I see our technology is really exciting is getting away from the stuff that is going to be encapsulated nicely in an organ, but things that need to be more pervasive throughout the body, but where you could still get those medical benefits of having embedded electronics.
Yeah, fascinating. Last question. Any parting advice for early or mid-career engineers who might be interested in pursuing the space?
I guess my advice would be do it. I've worked in a number of different tech fields, and to me, semiconductors are, the most exciting place to be at the moment, because it's just, they underpin everything. So whether you look at quantum, whether you're looking at AI, whether you're looking at net zero, you take almost any big trend at the moment, and, somewhere underneath all of that, semiconductors are what is enabling the changes. Come back to the first early discussion we had about, the AI machine learning stuff I was doing 25 plus years ago. That's all being enabled now because semiconductors have got good enough to implement it really, really well and accelerate that and make it happen in real time. So, yeah, to me, the excitement in semiconductors is just so massive. So, yeah, if you can, get into this and do more and help push that, then, what it can enable is endless.
Wonderful. Well, thank you so much for your time today. This was fascinating. That was Scott White, founder and executive director of Pragmatic Semiconductor. Thanks for joining me today in the lobby. I hope you found that as fascinating as I did. I honestly just want to go try to design my own flexible chip now. If you liked this episode, please let us know on the All About Circuits and Moore's Lobby social pages. I love seeing your comments, and it sure helps us grow this podcast if you share it with other people you think will like it, so that's always appreciated. And hey, what did the student chip say to the teacher chip after they explained a difficult concept? Oh, I see. Thanks for coming along with me today. I'm Daniel Bogdanoff, and I'll catch you next time.